hear a little background noise. That could be a little problematic. Oh, now hold on a second. Well, I just heard something. Just a second here. Say something again. No, I'm only hearing you. Wow. What did you just do? It took away all that interference.
I'm not sure.
Yeah, and I heard a sound on my GoToMeeting thing also. What's that?
Was it kind of like a screechy sound?
Well, yeah, all that interference was, but then there was a beep almost, like that. Did you hear that on my end? And then it all became better. I know that if you have your phone and checkbox where it says phone call. Instead of computer audio, check phone call.
Yeah, I did.
That should get rid of all that interference. Check computer audio. Let's see if that gets rid of it. I didn't change it any? Let's have you call me back. I'm going to hang up and just call me back.
Okay.
Hello? Yeah, okay. That seems to have helped a little bit. I don't hear that screechiness.
Yeah.
All right. Yeah, that's pretty good if we can get it to stay at that level there.
Okay.
All right. Okay. Yeah, this pictures work pretty good actually. With the technology of today, are you using an Apple iPhone?
Yeah.
Make sure you send it as a large image.
Okay.
In other words, once you get the image and you share it with Gmail, my Gmail address, send it as a large. If you send it as a small, it doesn't come, the resolution isn't good enough. But in general, the Apples take wonderful pictures.
Yeah.
You just have to have good light. Hold it about a foot away from the piece of paper when you take the picture.
Yeah. Now the camera on my phone isn't working.
Ah. You want to go round up your mom and dad and see if you can get them to use their phone?
Yeah.
Okay.
Mom, I can't use the camera on my phone. Yeah. Because of this thing. How do I send it to an email?
And like I said, once you send one, the next time you go to send it, you'll only have to type in a few keystrokes.
Yeah.
Okay.
All right. Let's see here.
That's David Cowan 1949@gmail.com.
Okay.
No spaces, caps don't matter.
Alright, it's sending.
Okay. Might take 30 seconds or so to get to me. How many pictures? Did you just send one picture?
Yeah.
Okay, there it is. Oh yeah, I've seen these problems. I actually have the full sheet on this problem here.
Oh, really?
Uh-huh. And if you want, you can back up far enough so that you can get all the problems on one picture.
Yeah, I did all the other problems.
Oh, okay, okay. Well, let's do this problem. What are we looking at? What's it called?
Oh, this sheet?
No, this problem number 2. That's the one we're doing, right?
Yeah.
Okay. It's not a full hemisphere, but it's a piece of a hemisphere, right?
Right.
Okay. What's the volume of a hemisphere? Or, yeah.
2/3 pi r cubed.
Okay. Well, we've got the radius, so we could figure out the volume of that hemisphere without the piece of cake that was taken out of there.
Yeah.
Well, what percentage of the full hemisphere do we have?
80/360.
Not 80. That would be the missing part.
Alright, so 480.
260 or 280 over 360.
Yeah.
In other words, we've got about 3/4 of it.
Uh-huh.
And that fraction is precise, 280 over 360. So that's going to give us our answer. And that's the way you kind of do all of these problems, whether they're volumes or even if I said find the measurement of the arc, no, find the arc length, excuse me, from A to B, and that's 80 degrees. Well, the arc length from A to B is a percentage of that circumference. So the first thing I got to do is find the circumference, 2 pi r, and then I'm going to have to multiply it by what part of the circumference do we have? Well, we have 80 over 360 in this problem here. And so we're essentially applying that exact same logic only to a volume.
Okay.
Fact is, we don't have a full hemisphere. We have 28/36 of a hemisphere. All right. What else?
I sent in a couple more.
Okay, cool. Let me pull them up here. Yeah, this works quite nice. I mean, the technology is pretty brilliant. That you can take a picture and in 2 seconds send it to me, and then we're both looking at it, talking about it, and solving it. Okay, number 11. You want to do 11 or 12 or both?
Let's do both.
Okay. 11. That's not a prism, but I tend to think of anything that goes to a point as being a prism, as being 1/3 of the prism. And let's just go over that. If I had a cylinder, that's the area of the base times the height, right?
Yep.
Capital B times H. Well, what if I go to a point, make an inverted ice cream cone? Okay? I have to shave away 2/3 of the material. In other words, if you gave me a right cylinder of soap and said sculpt a cone, I would shave away 2/3 of the material. What I'm left with is 1/3. So all figures that go to a point is the same volume as the volume of the prism would be, only 1/3 divided by 3. Okay? Well, what kind of base is that?
Octagon?
It looks to me like it's 7. I count 1, 2, 3, 4, 5, 6, 7. Okay, so I read it as a septagon. But what is the volume? We know it's 1/3 capital BH, right? So what's the formula for capital B? In other words, what's the base of that septagon? Deals with the apothem or the apothegm, however you pronounce it.
Yeah.
What's the formula for it?
You have the apothem, then the number of sides.
Like that. In fact, let's go over the area because there's two formulas. One is this. Apothem times the side length times the number of sides. But another one is sometimes, and you need to use this because they'll give you only the perimeter. Right. Notice that the side length times the number of sides is equal to the perimeter. So that's why this second equation is true.
Yeah.
But I saw a problem once where you couldn't figure out how many sides it was. They had drawn it in a way that you couldn't count them up. But what they gave you was the perimeter.
Yeah.
So they gave you an apothem and a perimeter so you could come up with the area of that base without knowing how many sides it had or what was the side length. Well, in this problem here, they give us a side length, and we can count that there's 7 sides. So, and they give us the apothem, 14.5. So it's going to be 14.5 times 14 times 7 times 1/2. Don't forget that 1/2. And that number is what goes in for base. Height is 33. It's always the vertical height. It's always the height from the middle of the polygon to the peak.
Yeah.
Problem 12. This is what kind of a figure? What would you call this?
It's half of the...
There you go, half of a cylinder. So the volume is going to be 1/2 base times height. Sounds like a triangle. I object a little bit with them using the letter B here, because capital B is an area. Little b is a length. And most people know little b as being the base of a rectangle, and that's the height of a rectangle. But here, little b is always measured in feet or meters or inches. Up here, it's always in square something. So these two b's are not even close to being in the same ballpark, so to speak. So what's the area of the base? In other words, if I'm going to use this, the volume of a cylinder would just be capital B times H. Since we have half of a cylinder, that's where the half comes from. And what's the area of the base?
37 by...
That's the height, 37. The height being the thickness between the two. That's a prism, actually. But
121.
yeah, 121 pi. In other words, it's pi r squared. And make sure you don't apply the half twice.
Right.
Because the area of that base is not 121 pi. The area of that base is half of that. And that's why I put that half there already. So there are a couple ways you could do this to avoid making a mistake. Maybe figure out the volume of the entire right cylinder, and then divide by 2 just to make sure that you aren't doing it wrong. But there's nothing wrong with this way. Okay, if I remember right, if I can think properly, I can probably pull this up from the other student, but just as easy for you to send the picture. How much, let's see, are we doing half-hour session today or an hour session? No, we got an hour scheduled, right?
Yeah.
Yeah. Okay, you want to send more pictures?
Sure.
Okay. Just holler when you've sent it.
Okay.
Yeah, this is the busiest Sunday I've had all year. It's because everybody's math finals on Monday. I've figured out. There it is. All right, a little trick, huh?
Yeah.
Okay.
I'm also sending a couple more.
Okay. The only thing we need to do on 6 is figure out that angle. Two ways you can look at this. No, that's not a right triangle. Okay. So you've done law of sines and law of cosines. Okay. You know both of them? You know both general formulas?
For which one?
Both? For law of sines and law of cosine?
No.
Okay. Well, let's talk about number, oh boy. Both of these are law of cosine problems. And there's only two kinds of triangles where you have to use the law of cosines to start it. And that is side angle side and side side side. Those are the only two. Well, notice 6 is side 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 and 8 is side angle side. So we're going to have to start both of these problems with the law of cosines. Now, even problems that you start with the law of cosines, your second step is always the law of sines. And the law of sines says this: the sine of any angle divided by its opposite side is the same within a triangle. The same ratio. It's not the angle divided by the opposite side, it's the sine of the angle divided by the opposite side. But in order to use the law of sines, which is by far the easier one to use, you have to have at least one angle and one opposite side. And notice we don't have that in problem number 6. You never do when you have side, side, side. And you also don't have it in problem number 8. And you never do when you have side angle side. So we're going to use the law of cosines.
Okay.
And the law of cosines says this. It kind of starts out like the Pythagorean theorem.
Yeah.
It's a good way to memorize it. And there's actually 3 of them, depending on which side you're solving for.
Yes.
What's the rest of that?
For the one starting with a squared,
Yeah.
a squared equals a squared plus c squared minus 2ac cosine of b.
Good. And the last one?
C equals a squared plus b squared minus 2ab cosine.
Okay. Now, let's do the one that makes the most sense first, which is let's do 8.
Okay.
Okay. Now 8 isn't labeled with A, B, or C. So I can just let that be the side I'm going to solve for. I'm going to call that Z. Okay. So Z squared is going to be equal to what?
8 squared plus 10 squared minus 2, 8 times 10 squared.
Not squared. Not squared, just multiplied together.
Yeah, and the cosine of 44.
Yeah, the side that's opposite Z.
Yeah.
And you'll notice that A, B, and C didn't have anything to do with anything. What you're doing is setting the side opposite the angle, squared, equals the other 2 sides squared minus all this stuff. Now, notice that everything on the right side of the equation is just a number that you can get out of your calculator. Okay, take the square root of that number and it'll give you Z.
Yeah.
So those are pretty easy. The side, side, side is a little harder. Do you want to do you need to go through this math, or are you comfortable with that?
I'm okay with that.
Okay, cool. It's always, setting them up is always the problem. Solving them is the easy part. So if we look at 6, where do we start? Well, let's start with that angle right there.
Okay.
X. So I'm going to start with this side. Okay, so I'm going to say 19 squared. Because I know on this end of it, I got the cosine of x, right?
Yeah.
Okay, so I'm going to use the 19 side since I want to solve for x.
Yeah.
So it's 19 squared equals what?
16 squared plus squared minus 2, 16 by 24.
This time I'd like to go through the math just to show you, because this time our variable is that.
Yeah.
So I've got to come up with a number for cosine of x. Then what am I going to do when I come up with a number for cosine of x to solve for x?
Now you do the multiply it by the negative cosine.
You take the inverse cosine of that number. So let's do that. You got a calculator handy?
I can go grab one real quick.
Why don't you? Yeah, it'd be better if you do these on your calculator than me,
Okay.
just to give you practice.
All right, hold on real quick.
Okay. Go ahead and do each of these calculations. Square 19, what's that?
361.
16 squared.
256.
How how much?
256.
And 24 squared?
576.
And 2 times 16 times 24.
768.
What's the next step? Add these two. What's that give you? 832. Now what's the next step?
So you got 361 equals 832 minus 768 cosine x. So then you subtract 768 from 832.
Not 768. It's the multiplier. What number is being added to this? In other words, we're going to initially solve for that. We're going to isolate that. So we have to get rid of everything that's attached to it. Well, we got an 832 that's being added to it, and we got a 768 that's multiplying it. So let's get rid of the 832 first. What's 361 minus 832?
Negative 471. Yeah.
So, did I do that math right? Yeah. And that's equal to negative 768 cosine x. Now divide by the negative 768. What do you get?
Divide by negative.
Put some room here.
0.6132.
So, if the cosine of x is equal to that decimal, x is equal to what? The inverse cosine of that decimal.
So you get 52.1. You get 52.2.
Okay, degrees, and that solves the problem. I don't know whether they wanted you to round off to the nearest hundredths place here or what, but whatever they want you to round off to, do it. Now, occasionally, now notice what we have, okay? This problem said solve for x, but frequently these problems say solve the triangle. In other words, they give you 3 pieces of information always, and then they want the other 3. There's 3 angles and 3 sides to every triangle. So once I have x, now the next step I'm going to use is the law of sines, because I have an angle and its opposite side. And once I have that, it's much easier to use the law of sines than it is to do anything else. So I would be able to come up with one of these other angles using the law of sines. And then finally, the 6th piece of information, the 3rd angle, you don't need to use either law of sines or cosines. Just subtract the other 2 angles from 180. And that'll give you that 3rd angle. Okay, now, every now and then, you'll get a problem and you'll come up with this kind of an answer. Try to find the inverse cosine of 1.1. Undefined. Did they say undefined, or did it make your computer go crazy? Or your calculator? Yeah, you must have a TI-84. Yeah. The Inspire will actually say undefined. The reason is that there is no such angle that the cosine of that angle would be equal to 1.1. So what's happened is they've given you an impossible triangle. Let's talk about triangles for a second. Is that a possible triangle? No. In other words, the rule, and tell me if you know this, but any side of a triangle has to be less than the sum of the other two sides and greater than the difference of the other two sides. Well, you knew this wasn't a triangle because 5 is not less than 2 plus 2. Well, if somebody gave you this triangle and they said, okay, solve it, let's use the law of cosines. When I go through this exact process that we just went through, you're going to end up with the cosine of x being a number greater than 1 or less than -1. And that's how you know that it's not a proper triangle. I mean, other than the other way. It's nice to know both rules, but the other one comes in handy sometimes because you may not recognize that it can't be a triangle. And when you go to solve it, if you ever see sine of x is a number greater than 1 or less than -1, impossible. Same with cosine. In other words, if we look at the cosine curve or the sine curve, it just fluctuates between 1 and -1. There's 1, there's -1. You'll notice nowhere on that curve is it ever greater than 1 or less than -1. And cosine curve does the same thing. Starts at a different place, but it just keeps fluctuating back and forth. So it's impossible for the sine of an angle or the cosine of an angle to be greater than 1. Tangent, not so. Tangent can be 1,000,000. Here's the tangent curve. Goes up to plus infinity and goes all the way down to negative infinity. So tangent's not restricted, but sine and cosine are. So let's see, did we do everything we needed to do on both of those problems? Yeah, we completely solved 6, at least for x, and we saw the solution for c. But this is what happens. These are the only two type triangles that you use the law of cosines, and this one's easier because your answer comes out on the left side of the equation, all as a letter. This one's harder because what you initially solve for is the cosine of that angle, not that angle. And once you solve for the cosine of that angle, it requires that last step where you take the inverse cosine of the number to get the angle. We always take trig functions of angles to get ratios, and we always take inverse trig functions of ratios to get angles. So when you're solving for an angle, you're going to have to use inverse at some point. Okay, let's say you say you sent me a couple, didn't you? Yeah. Let me bring up the next one. Circles. How are you on your general equations for all these circles? There's got to be 20 general equations that apply to circles, tangent lines, chords, secant lines, measurements of arcs, arc lengths, segment lengths. I'm tempted that the best way to review for you is for you to just go through all the general equations. Let me spit out the thing and you tell me the general equation. Unless they let you have a cheat sheet. I doubt that they do, though. No, you got to have all these memorized. Okay, so let's do it that way. Rather than solve these 3 problems, which would be useful, but not as useful as this. Two intersecting chords. The lengths of these chords are A, B, C, and D. What equation applies?
A times C equals B times D.
Good. That's intersecting chords regarding segment lengths. But there's also intersecting chords regarding angles. Here, let's put a B there. What's the equation that applies here? And I always start out with the angle. In other words, what is 140 degrees equal to?
I'm not sure.
It's 1/2, which is very common in most of these, the sum of the two measurements of arcs that were intercepted. So that's the sum of arc ABC plus arc AC. Excuse me, not AC. AD. In other words, this 140 degree angle intercepted arc ABC, right? And the other side of it, which is also a 140 degree angle, I labeled this wrong also. It's ED. My error, sorry. It's not the whole circle. In other words, it leaves out these two little arcs here. So it's the big arc plus the little arc. It gets intercepted by both of those angles. Okay? That covers intersecting chords pretty much. Now, the situation that's quite different is when you have intersecting secant lines outside of the circle. Let's talk angles first, and then we'll talk segment lengths.
Okay.
What's theta equal to?
Half.
Good.
A for arc AB minus arc CD.
Correct. In other words, when the intersection takes place outside the circle, it's going to be subtracting the two arcs, not adding them. The only one that I can think of where you add them is when you have two intersecting chords inside of a circle. Okay, now let me erase these letters and let's talk about segment lengths when you have two intersecting secant lines. This little segment will be A, that little segment will be B, this little segment will be C, and that will be D. What equation applies here? It's not the same as chords. In other words, the most common mistake here is to say A times B is equal to C times D. It is not.
Isn't it A times A plus B equals C times C plus D?
Correct. In other words, it's the segment outside the circle times the entire secant line. And this segment outside the circle times the entire secant line. Okay? Now, I'm going to give you one that's very similar and is actually exactly the same. And that's when I have a secant line and a tangent line. Okay? If I knew that angle, well, that angle is going to be 1/2 of the difference between these two arcs. That one and that one, right? Those are the two arcs that are intercepted, the big one minus the little one. And if we look at segment lengths, I'm going to put an A there, a B there, and a C there. Well, it actually follows this rule, even though they give you a completely different theorem for it.
You just square the C.
You do, but notice that that's the same rule. In other words, I'm taking A times the entire secant line equals C times the entire tangent line. So I've got A times A plus B equals C times C. or c squared.
Yeah.
And like I said, this is usually given to you as a separate, completely separate theorem, but it's actually the same thing as that. That tangent line is no different than a secant line. Okay. What's true about two tangent lines intersecting outside of a circle?
The measures of this?
Yeah,
Are equal?
A is equal to B, always. What's true about a tangent line intersecting a radius line? What's this angle?
90 degrees.
Always. You cannot have a tangent line against a radius line without it meeting at a 90-degree angle. Okay. The two simple ones that I didn't really start with, I probably should have. A central angle always intercepts what size arc? That 40-degree central angle? That intercepts a 40-degree arc. If you intercept the same arc only with an inscribed angle being one where the vertex is on the circumference, not at the center, what's this angle here equal to in terms of that arc?
20.
Correct. 1/2 of the arc. Okay. Let me look at your problems here and see if I see any that I've missed. Let's see. So, angle H is what? It's 77, but it's actually half. Here, let me do that one because I didn't cover that one either. Let me draw it a little differently.
It would be half 77 plus 77.
You got it. And why is that true? Because angle 1 and angle 2 are supplementary, correct?
Yeah.
And angle 2 intercepts that much of the circumference, and angle 1 intercepts the rest of it. So together they intercept 360 degrees always. So therefore, each one of them must be half of this measurement. So that's why in your problem, angle H is 77, because it's actually half of 144. No, that's not even a tangent line. I didn't even see that 26 degrees over there. Well, that's just the same thing as we did cover. In other words, that is an inscribed angle. But that's okay, because the other thing that I just showed you is another problem that you have to be able to do also. Now, in this problem 6, the only thing they gave you was this 26, right?
Yeah.
So we know that's 26. We also know that that line goes through the center, so it's a diameter line. So this is 180.
Yeah.
So we actually know that that's 144 immediately.
Yeah.
I'm not sure that it really breaks up into 77 and 77, to be truthful with you. It might, but you wouldn't want to do it that way anyway. In other words, given H and 26 degrees and a diameter line, you would immediately just go label that, oh, and it's not 144, it's 154. Oh, that's, okay, right. What am I thinking? Yeah, so it's 154, the measurement of that arc.
Yeah.
And since h is half the measurement of that arc, h is 77. But I don't think it's necessarily true. In fact, it isn't. I could move this point any number of directions without changing the angle h, right?
Yeah.
In other words, if I put that point right there way over here, then I definitely do not have two equal arcs, but I got the same angle h.
Yeah.
So these are not each 77. At least there's no way to figure out that they are. Even though they look like they are, kind of. Okay, for lengths, notice that all of our questions on circles are in either talking about angles or degrees, arc measurements, or lengths of segments or lengths of arc measurements. Okay, well, number 8. Oh, they give you the length of the arc and they ask you, okay, let's take a little more.
Just divide that by 2. 7 equal to 63.
No.
Wait. Oh, because of that. How do you get the area?
Well, that's a good question. You got to somehow figure out the radius. Or, oh, I can figure out the radius. Okay. Now I got it. From that 63-degree angle, what is the measurement of that arc? From here to here, based on the fact that that's 63.
126.
Correct. What fraction of the circumference is that? If that's 126 degrees,
Okay. So,
how would you get the fraction of the circumference? What's the full circumference? How many degrees?
60.
So that represents this fraction of the circumference, right? Well, the circumference is 2 pi r. So I can say that this fraction of the circumference multiplied by the circumference equals 7 pi. Okay. Now that allows me to solve for the circumference. So that's the only variable. Once I solve for the circumference, now I can solve for the radius. Once I solve for the radius, I can solve for the area. So this is actually a really good problem. Yeah, this incorporates all kinds of things in it that eventually allows you to solve for the area. But all of these problems, notice they start out with a general equation, and usually only one variable. I haven't run across one yet that has two variables. Either the variable is you're solving for the arc length, or the variable is to give you the arc length and you're solving for the circumference and then the radius and then the area. But they all depend on you knowing these general equations. If you know your general equations and start out every problem with the general equation and then just start filling in what you know.
Okay.
In other words, the general equation here, let me be a little more specific, is arc length equals the circumference times the percentage of the circumference that you have. And that is the measurement of the arc divided by 360. Well, we first had to get the measurement of the arc. That gave us this. And they gave us arc length of 7 pi, so I can fill in that. So I'm able to get to this step relatively easy. And then 2 more steps to go. But there's like 5 steps to get the area of that circle.
Yeah.
Yeah. All right, Kit, I have another one at 5, so I'm going to have to run. But
Okay.
this was your first online session?
Yeah.
Oh, well, good. I hope it worked out good for you.
Yeah, it did. Thank you.
Yeah, these are pretty cool. It's amazing what technology can do these days.
Yeah.
And that was without you even having a microphone on your computer. So, all right. Well, good luck on your quiz.
Thank you.
And have a good summer if I don't talk to you. Maybe next year.
Yeah, thank you, you too.
Okay. Bye-bye.
Bye.